Hi, everyone. My name is Howell Curtis from satsearch, and I'd like to welcome you to our webinar, A Guide to Selecting an ADCS for a Small Satellite Mission. In this event, you're going to hear from experts from 6 different ADCS manufacturers, discuss their technologies, their missions, and share insights on how engineers can better integrate and use their equipment. I won't say much more than this because it's them that you really want to hear from today. I just want to let you know 3 things quickly before we kick off. Firstly, we're not going to be running an audio Q&A during the event to try and keep things short for everybody, but instead, we've asked all the presenters to respond to questions in the Zoom Q&A function. So you should be able to see this on your screen. So please feel free to ask questions at any time of any of the presenters, and they'll try to answer them when they can, when they're not speaking, of course. Secondly, if you've got any questions or things to share with other members of the audience today, not the presenters, on the topic of ADS solutions, then the Zoom chat function is open throughout, and you can use this. And we'll also share links to each presenter's satsearch supplier hub in the chat function, so you can find out more about the company and take a look at their products and services. If you've got any other technical or procurement related requests, more specific requests, then please feel free to use the satsearch platform to make them. And finally, we are recording the session, and we'll also soon hopefully be getting access to the slide decks of each presentation. And so we'll send you a follow-up email with that information, that material, probably next week. Okay, that's all from me for now. Thanks to all of you for being here, and hopefully we'll have a great event now. So without further ado, we'll get straight into our first presentation, which is by Torvin Dilaby, the CEO of ArcSec. So Torvin, if you could share your screen, please.
Yes, I hope you can see it now.
Yeah.
Yes, perfect. Okay, so then I guess we'll just kick things off. So, well, good afternoon, everyone. So my name is Torvin Dilaby. I work at ArcSec. ArcSec is a spin-off company of the KU Leuven University in Belgium. We were founded last year, so we're still quite a young company. And we develop attitude determination and control systems for small satellites. So that's basically all we do. That's our focus. So we develop full attitude determination and control systems, which autonomously take care of all the attitude determination and control needs of small satellites. And we also develop standalone star trackers and reaction wheels. And it's really our goal to deliver very high accuracy attitude determination and control systems. On the left, you can see our larger star tracker, which is around 40 by 50 by 95 millimeters. And on the right, one of our new products, the mini star tracker, the Twinkle star tracker, which is about the size of a matchbox car and which delivers very high accuracy as well. We have flight heritage on Simba, which is an ESA IOD 3-unit CubeSat, which was launched 1 year ago. The ADCS was fully functional from the start. It contains, well, all the components that we made ourselves. Our reaction wheels work well. The star tracker, as you can see on the right, so this is the overall performance over the entire year. That one has a cross-bore side accuracy of 10 arc seconds, 1 sigma, and the Sagitta that I just showed you will go down to 1 arc second, 1 sigma cross-bore side. So quite high accuracy, and well, it's proven to work in orbit. But so, well, it's not a sales talk, so I won't go into a lot of details about our components. You can contact me or go to satsearch or go to our website. So I tried to make my presentation quite educational. So I start, I picked 2 topics to discuss. So rather than giving a lot of more generic hints on selecting an ADCS, I'll be talking 1 about determining the pointing requirements, which I think is an important point, and 2 on integrating, testing, and calibrating ADCS components. I could talk about a lot of things more, but and you can contact me and ask questions about it. But so I selected 2 things to discuss in detail, with point number 1 being the one that I will spend most time on. And the reason I chose this point is that there are quite a few sources that can tell you what you can get in terms of ADCS. And I guess everybody who presents here will start their presentation with saying what they can deliver, and you can find it on satsearch and on other websites as well. But the first question you have actually is what ADCS does my mission need? And I'm going to try to give you a bit of a framework to determine what you need in terms of attitude determination and control system. And it's an important thing because if you underspecify your ADCS requirements, then your satellite won't be able to do what it needs to do, but well, your ADCS won't be overly costly. But if you overspecify it, then well, your satellite might achieve its point, but the ADCS is overdimensioned and costly. So it's important to find the right specifications for your mission so that you can select the right system. So the pointing requirements that we typically get from customers look like this. So the ADCS shall deliver a pointing accuracy of 0.1 degree. And it looks fine. And I guess most of the people who are watching the webinar will probably define their requirements in this sense. But it's lacking a lot of stuff. So I'm going to try to expand this and give you a way of formulating your pointing requirements that will allow you to improve them. So a good pointing requirement contains a specified error value. That one is available, so it's 0.1 degree. But it should also specify in which reference frame you define it. So for example, on all three axes, or maybe you want it only on one axis and you have on one axis and you have less stringent requirements on the other, or you only want it on the payload line of sight. So as an example, I define that it should be half cone along the payload line of sight. It should also have a level of confidence, because if you just say that it should be 0.1 degree, then in theory, it should be that all the time and your system will be extremely expensive. So here, for example, it's 2 sigma, so 95% of the time it needs to adhere to the requirement. And you should also define which type of error it is. So here it's, for example, an absolute pointing error. It could also be a relative pointing error. There are some others, but they are, I would say, less common. To show you what that actually means, so an absolute pointing error, so if you have a system that requires an absolute pointing error, then that's the actual difference between the true and the desired attitude. So that's the big black line on this graph. You can then, over a certain period of time, take the mean of that and define a relative pointing error, which is also called the jitter, which shows the fluctuation around that mean. And to show you what each of those things does, if you have, for example, a disaster monitoring mission, so there's a forest fire somewhere and you want to take a picture of it, you need to have your absolute pointing error low enough to ensure that you're looking at the correct scene. If it's too high, you will be pointing off from the scene you want to see. But even if your absolute pointing error is okay, if you have a high relative pointing error, then you will shake a lot. Let's say, for example, that you take an observation time of 1 second. So typically the integration time of your camera, for example, 1 second, it would generally be lower, I assume. If your relative pointing error is too high, then you will have a blurry picture. So you will also want to define a relative pointing error requirement. What you also need to define is the period in which your requirement needs to be followed. So if, for example, only an eclipse, or only during a ground station pass, or only during the 5 minutes that you observe a star, whatever. Okay. So once you define your pointing requirements this way, so if you use this framework to define what you actually need, then this way of thinking will force you to think about your requirements in a bit more detail, and it will prevent over and under specification. And in the end, you might end up with 20 pointing requirements instead of the one that you had before, but still it will be better specified and it will not be over specified anymore. And once you've done this exercise on your side, then it will be much easier to select an ADCS system that really does what you need to do. So I look forward to getting like these very detailed pointing requirements from customers. Of course, it's not a sales talk, but you need to sneak in a little bit of sales. This is something that we can help you with. So we've done this for several ESA IOD missions, also for several customer missions. So we can define pointing requirements based on the description of the mission. We can also carry out a pointing analysis to see with which ADCS you can get which accuracy. We can do stability analyses. So those are all things that we've done before, and that we can provide as a service. The second point then is, so I talked about pointing requirements, which is something that you need to do at the start of your mission. Towards the end of your mission, once you have your ADCS, you're going to want to integrate it, test it, so commission it. And the point that I would want to make here is that the purchasing cost is often an important driver in the ADCS selection. So if two systems are almost equal, then especially for CubeSats and small sats, the purchasing cost will have quite a high weight in determining which system you choose. But what's often forgotten is that there's a substantial cost linked to manpower, to equipment, to facilities for integrating, testing, and calibrating the ADCS. So once you, if you just get the ADCS in a box at your office, then there's still a lot of work to be done to integrate it. So what I would ask, or what I would urge you to do, is to ask your ADCS component provider, not only to send you the ADCS, but also to provide ground support equipment or software, graphical user interface software, for example, to facilitate the integration. So preferably, you would not only get an ADCS or a star tracker or a reaction wheel, but also the supporting equipment, so that you can just, in the ideal world, hook it up to your computer and have a plug-and-play system that you can work with, or get some libraries that you can integrate into your overall satellite system so that you can easily start working with it. What I would also urge you to do is to ask for the functional test procedures and the ability to replicate the acceptance test campaign at your site. So typically ADCS providers will carry out a quite thorough health check test or acceptance test before they send the unit. So I would urge you to ask one for procedures, how to repeat that, and also make sure that you have the ability to replicate those. Because once you can replicate them, then you're quite sure that you can work with the system and you know that you have a healthy system. And as a third one, it's really interesting to have a reprogrammable system, not only in the lab, where if you see that some functionality is lacking, or you would have preferred to have something implemented a little bit differently, but also in orbit. So we recently did a small software update on our ADCS to tweak some performances. And it's really useful if that's possible. So those are three things that I would urge you to look out for, and also to take into account that this can greatly reduce your development time, project cost, and also just make you a happier person. And of course, all of this is standard included in what we deliver. So I haven't made it a very long presentation, so I just focused on 2 points. One is on helping you to determine your pointing requirements. So yes, make your requirements less dumb is something that we hear a lot. And the idea that I want to give you there is that if you use the correct formulation for these requirements, then you will get your project right from the start. And for integration, testing, and calibration, take into account that it's an important cost driver. So ask your ADCS components to give you as much support as you can get. And that was it from my side. So if you have any questions, you can contact me. Thank you.
Great, thank you very much, Torben. That's a fantastic way to start. So yeah, how to make good pointing requirements, very useful, and then really good advice on integration and testing there. Thank you. Next up, we have Gerhard van Vieren, Principal ADCS Engineer at Cubespace ADCS, based in South Africa. Gerhard, if you could please share your screen and get underway.
All right, my screen should be shared. Can everybody see it? Fantastic.
Yep, that's good to go. Thanks.
All right. So what I'll be talking about today is firstly just a quick introduction of our company. Then I'll talk about which factors influence an ADCS system design. There's often this decision that integrators of satellites face, whether they should buy off the shelf or build it themselves. And I'll talk a little bit more about the pros and cons of each of those, and then some lessons that we've learned, along with some interesting real-world examples. All right, so first off, our company is also focused on ADCS only products. Our first flight was in 2014. We've served more than 50 missions currently in orbit. We're located in Stellenbosch in the beautiful South Africa. We've delivered more than 1,000 products to more than 100 customers globally. We offer fully integrated ADCS solutions, so everything, including hardware, software, harnesses, ground support equipment, everything that you'll need, even a simulation tool for your ADCS. We also offer standalone components if you prefer the build-it-yourself option. Those include reaction wheels of various sizes, from 2U up to small microsatellites. The same goes for our magnet walkers. Then we've got some fine sun sensors, infrared horizon sensors in our Generation 2 product range, star trackers and magnetometers. There's a nice link about our Gen 2 product range. I believe it's a video. Please have a look if you receive the slides afterwards. Our facilities include an ISO Class 8 clean room and a dark room where we calibrate our optical sensors, such as the star tracker and our fine sun sensor. We've got a Helmholtz gauge to calibrate the magnetometers, vacuum chamber with thermal control, some thermal chambers in our production facility with humidity control. We've got our own vibration table, which was recently added, as well as a couple of staff that are IPC Class 3 trained. That's enough for the sales talk. I'll get back to the engineering, which I'm more comfortable with. So the first thing that I want to talk about is how requirements influence your ADCS design. What we've noticed is that different levels of requirements influence the ADCS design. So we've got the higher level emission requirements, then the derived system requirements, and then ultimately the lower level ADCS requirements. And all of those can in some way impact your ADCS design. And what we've noticed is that the typical top-down requirements model doesn't seem to work for the modern small sat or nanosatellite missions. It's not as simple as laying down requirements on a mission level, freezing them, moving over to system, freezing them, and then having a subsystem requirements, and then just building a system or procuring a system that meets all of those requirements. There are very often trade-offs and concessions that need to be made on all levels because the hardware just isn't out there, or we just can't build exactly what the mission needs. So ultimately, you'll work your way towards the ADCS requirements, come up with an ADCS design, but often you'll find that what is out there in the market or what you're able to build in the amount of time that you have won't meet requirements A and C, but it will meet the most important one. So we'll be willing to drop this one or make it less strict. So it's a very iterative process, at least in our experience. Then when it comes to component selection, once you've solidified the design, it flows down mainly from your ADCS requirements. You've got the decision of how many of each sensor. Once you've for example, identified the need for a star tracker, do you want to add a second one for redundancy? Do you have the budget to do that? When it comes to actuator sizing, your wheels and torquers need to be sized depending on your satellite size, the type of orbit that you're going to be in, the type of deployables that you'll have, the direction in which they're deployed. That will determine your in-orbit disturbances, which will affect the size of your torque rods. If you've got a very high slew requirement, so your satellite needs to be very agile, you'll need larger wheels with more torque or more momentum storage capability. And then something that I'm very excited about is component placement. That's where you get to work with the customer's CAD and really try to figure out a tailored engineering solution for their specific mission. So you've got, let's say, 5 or 6 different ADCS sensors, but you've also got a satellite design with a panel sticking out in this direction and an antenna sticking out in that direction. And you need to find a spot for each one of those sensors and make sure there's actually available panel area for a sensor to protrude through. You've got the sensor field of view to take into account, especially when you're using deployable structures. And then you've also got to take into account which ADCS modes does your payload require, does your antennas or your comm system require. So if you've got, for example, a star tracker pointing in a certain direction, but you've got an antenna which needs to face a ground station, will that star tracker still see stars, or will it point at the Earth when you point your antenna at the ground station? And those are things that not all customers seem to think of when they're buying or procuring their ADCS. And we've often seen that satellite designs need to be changed very late in the mission, just because these type of things weren't taken into account early enough. When it comes to the buy versus build decision, there are three main options. You can either buy the entire fully integrated system from a third-party supplier. You can buy standalone components and then build the system yourself. Then you've got to think about your software that's going to run the system. That, I believe, can also be outsourced. I'm sure there are companies out there that do that. And then you can build the entire system yourself. So from the ground up, build everything, or at least most of the components yourself. In this decision, there will be various stakeholders. So on the lowest level, you've got the technical stakeholders. If you cannot find an off-the-shelf solution to meet your requirements, you'll obviously want to go for the build-it-yourself solution if you've got the technical capability to do that. From a commercial perspective, the company might want to push outsourcing rather than vertical integration, which will lean more towards the buy decision. And then you've got, of course, the programmatic stakeholders, which will push timeline the most. And if your timeline simply does not allow a self-build option, then you have to go for a buy option. But in principle, there are three main factors when deciding whether to buy or to build, and that's risk, time, and cost. Unfortunately, I can't provide a nice one answer or one-liner for whether or not you should buy or build. Every mission is different, and there are pros and cons to buying versus building. I'll start with the pros of buying. The first and most obvious pro there is that you'll leverage years of ADCS experience, not only from the supplier, but also from other customers that have flown this supplier's ADCS. It's in most cases the shortest lead time, and there's virtually zero development cost. There are cons to buying a system. It's not always optimized for every mission. The suppliers generally build a generic solution which can fit most missions, and it's not tailor-made for your specific mission. And you're going to be dependent on a supplier, one or more suppliers, which is not necessarily always a good thing. Then you could argue that there's a higher cost per system versus building it yourself, but then you're not taking into account the massive NRE, the non-recurring engineering cost that you'll have to incur when you build it yourself. There are good things about building an ADCS yourself. You can tailor make the system for your specific mission. You've got no dependency on any third party if you choose to build everything yourself. And it's a very, very nice vertical integration strategy to get all of that development in-house if your company supports that strategy. But there are, of course, cons to building it yourself. I've mentioned most of them. You'll firstly require a whole development team, ADCS engineers, electrical engineers, mechanical engineers, and software engineers. Those are all the components that make up an ADCS. The development time is usually in the order of years if you've got a very narrow solution that you're working towards. It could be less than a year, but it's usually in the order of years to develop a full ADCS for a larger mission. You've got massive investments or non-recurring engineering, and there is, of course, increased risk because you'll build something that's new, which has a very low TRL. There are many options out there, and you'll be wise to choose carefully. Things to consider is reliability and what the TRL of the system is, and whether or not there's evidence, so qualification reports, in-orbit reports, the reputation of the supplier in the industry, which other companies are using this system or the supplier, if you can find information like that out there. how stable is that supply chain? How long is the lead time, not only for one or two off, but if you expand your company and you start ordering 10 or 20 or 50 units at a time, can your supplier handle that? Will they still be around for your next mission? It's also a question you need to ask yourself. And then most importantly, does the integration into your mission of that system make sense? You'll have to take into account mechanical integration. How does the system get bolted onto your spacecraft? What's the electrical and the software interfaces? Are those configurable at all? And how much effort is it going to be on your side to accommodate that system? Which ADCS modes are available? Can that be expanded? If you've got a very custom control mode that you want, can your supplier implement that for you? And how easy is it to operate the system? Then something that you'll thank yourself later for is checking the support structures of the supplier. How well is their documentation? How much support equipment do they give you, both hardware and software? And how can they support you during commissioning and operations of your system? I'm listed cost here on the right, but I put a little band sign on it, because even though cost of ADCS systems are fairly large and you'll want to go for something that's cost effective, all these other considerations are much more important than cost. You'll end up spending a lot more in man hours if you don't pick a supplier that meet all of your needs in these other areas. Then just lastly, some lessons that we've learned in the process of building an ADCS. And we're recently, with our Generation 2 product line, come across this quite often. And that's, if it's new, it usually takes longer than you expected. So it's good to always add margins. And that includes when you're building your own spacecraft, adding margins for lead time from suppliers, adding margins for testing your ADCS and calibrating it on ground, if it's something that you're doing for the first time. And lesson we've learned as well, hire good project managers to make sure everything happens on time and everything is taken into account when you're planning your project. You rarely get it right the first time if it's something that you're doing that's new. Allow for mistakes to be made and add a margin or extra buffer into your timeline for additional design iterations. And I cannot emphasize testing your system enough. Test it for race conditions, for edge cases, test it in a realistic in-orbit environment. And that ties nicely in with my last point. You must have a simulation tool if you're going to be building an ADCS. You need to know how your algorithms will interact with the space environment, how it will interact with the satellite body, and having a proper simulation tool that can tell you what your modes and your configuration will do under certain conditions is a must. During test and integration, we've also learned a couple of lessons. I'll just quickly run through those. So there's a very big misunderstanding in general about the concept of an ADCS coordinate frame versus just your normal mechanical CAD frame. We often see customers not taking into account that the ADCS has its own built-in coordinate frame, and it, with its own sensors, has a certain knowledge of how the satellite is oriented in orbit and what does zero roll pitch in your mean to the ADCS. And that's not necessarily the same as your X, Y, and Z definition of your mechanical CAD of the satellite. So make sure you know what the translation between your frame and what the ADCS thinks the frame is. The most important sensor of your satellite is the magnetometer, except for your payload, of course. But in the ADCS, that's by far the most important. If you don't have something like reaction thrusters to desaturate your wheels, you need to use magnetorquers to desaturate your wheels. If you don't have a proper magnetometer measurement, you can't use your magnetorquers properly. Magnetometers are easily disturbed and disrupted by sources such as solar panels, fasteners, your EPS, electromagnetic valves, and which is why we normally recommend a deployable magnetometer as well as adding a redundant magnetometer. And important, test your spacecraft in all operational modes. There might be a payload or a subsystem that's only used in certain scenarios, and it might generate a significant magnetic disturbance, and you want to make sure that you capture all of those operational modes when you're testing your magnetometer on ground. And if you're having, moving on from the magnetometer, if you're having deployable appendages such as antennae or solar panels, make sure that when you have sensors with a field of view, such as a sun sensor or a star tracker, that you don't have any of these sensors in their field of view. I know it sounds obvious, but we often see customers that don't take that properly into account. And then lastly, for test and integration, we've often seen problems with EMI. Those have to do either with ground loops, where different grounds, either from the chassis or the structure, or from antennae, are just connected at random with other grounds, and you eventually form ground loops, which firstly disturb the magnetometer, but secondly causes noise on power lines, which can affect components like star trackers in terms of its measurement accuracy. And then for EMI, we've often seen cases where long harnesses are used, and the notorious I2C bus of CubeSats is especially susceptible to EMI. There's a good example where a satellite designer had an ADCS on the one side, an EPS sort of perpendicular to that, with a harness running from the ADCS across the EPS to a magnetometer. And the magnetometer's measurements were continuously corrupted because of the EPS currents being generated and causing EMI interference on the harness. And the eventual solution was to shield the harness. So watch out for that when you're integrating and planning your cable routing in the satellite. Some learnings from in orbit. Adding margins to exclusion angles specifically for star trackers is a good thing. We've learned from some in-orbit images that the atmosphere is clearly visible in eclipse to star trackers. It's of course not intentional to take a picture of the Earth, but when you do take exclusion angles of the sun, the Earth, and the Moon into account, it's always good to add a little bit of a margin in there. So with the atmosphere, instead of having the Earth's edge be your calculation point for the Earth exclusion angle, rather use the atmosphere, which in the images that we've seen is roughly 70 kilometers from the Earth's atmosphere that's actually visible in a star tracker image. Very faintly, but enough so to cause disruptions to the algorithms. It's very necessary to have a safe mode, especially for high spin rates. We've seen cases where multiple cases of satellites being accidentally spun up, either by an operator error, accidentally firing a thruster, and having an ADCS with a safe mode capable of tumbling from very high rates it could be mission saving. So take that into account. And then lastly, but I couldn't stress it more, check the polarities of sensors and actuators. In the very early days of our ADCS expeditions, we almost had a case of a torque rod being flipped in polarity, and luckily that was caught very close to integration. But make sure that you firstly check polarities of actuators on ground, but then secondly that you have the ability to swap polarity in orbit if that's ever needed. That was it from my side. If you do have questions, pop them in the Q&A section. I'll answer them as I have time. If you've got more questions, feel free to reach out to info@Cubespace, and yeah, we'll answer them as they come in. Thank you very much for listening.
Great, thank you very much, Gerhard. That was really interesting. I think the great take home at the end as well. Spin up, not spin down. Really important for spin outs as well. Yeah. Next, we have James Barrington Brown, CEO of New Space Systems. So, James, when you're ready, if you could please share your screen. Thank you very much. That's perfect.
Thanks. Off mute and seeing my screen. Thanks very much. Yeah, some very wise words there from the previous speaker. I'm glad, or at least I'm hoping so far people have been talking about the ADCS control algorithms themselves. I'm an electronics engineer, not a control engineer, so I'm going to be talking a lot about hardware and electronics. Yeah, just a couple of slides from Cubespace. Our heritage goes back to 2008, where I set the company up in the UK, moved down to South Africa in 2013, started up 2014. Quite near Cape Town, actually not too far from Cubespace, and we're exporting also all around the world, 27 countries last count. And we're baseline on a number of what I call recurrent platforms, which means prime contractors who are supplying different missions to different end customers who basically use the same platform architecture, and they're using our components for those kind of things. I mention it because I'm now just over 30 years in small sat business, and it's amazing to have seen the growth in the last few years. I mean, back in the day, there was maybe only 20 primes you could bid to, and now there are several hundred, I believe, especially include the university groups who are doing CubeSats. So what do? We do ADCS, and that's why we're on the talk. So sensors looking at stars. We have a unique product called Stellar Gyro. Sun sensors, the Earth we detect using magnetometry. On the actuator side, we're doing reaction wheels. And we believe, still yet to hear anybody contradict this, that we're the largest torque rod maker in the world. We won the OneWeb contract and a couple of other constellations. So we're churning these things out 1,000 a year. So very high volumes. To know where you are in orbit, people haven't mentioned that much yet. But part of an ADCS system, you need to know where you are. So we do GPS receivers and the antennas to go with them. And we train our people up to the European Space Agency standards. So we also have some people just using us for manufacturing. So I'm going to talk about scaling up because I see a lot of the talk, the presenters here are from the CubeSat community. We're very much in the microsat community. So I wanted to talk about some of the issues when you scale up from the smaller systems to the larger systems. And you basically have a matrix of 4 different options. You can have integrated hardware with the algorithms built in. You can have integrated electronics without the algorithms. And I'm just going to do a little plug for this. You're the first people to see this little box on the right. A box is a card. It's actually a magnetic control system for CubeSats, which we've managed to get into a very sexy shape, mainly because we've come up with a way of generating magnetic fields using flat electromagnets. So the electromagnets and the X and Y are actually buried into the structure, leaving a nice hole. So you can put your wheels, you can put a camera through the middle, put a star tracker through the middle. So yeah, that'll be coming out soon. And then of course we deal with components, and I'll show you some solutions, components with the algorithms built in and also without algorithms. So in terms of scale up, we're seeing a lot of our customers are starting off with CubeSats to do some kind of payload demonstration or mission demonstration, things that you can't really do on the Earth. And then they tend to be moving up when they move to operational systems into the larger end of CubeSats, 6U, 12U, and also into microsats. And of course, as was mentioned earlier, the actuators will scale with mission size. The larger the mission, the larger the actuators you need. And of course, when you get to a bigger volume, if you need to have omni coverage, for example, looking at the sun, then your sun sensors can't be put into the same box. They need to be mounted on the panels either side. So you get into some of the harness issues that we just mentioned. Maybe someone will talk about different architectures of OBCs, but you can have a single computer which does everything in the housekeeping. The attitude control system controls the payload, or distributed systems where you can have a dedicated computer just for attitude control. I'm very much of the mind of distributed systems, so put as many computers on your satellite as you can, each having their own tasks. But some people now are, for example, taking their star mapper algorithms and putting them on an onboard computer rather than the algorithms sitting inside the star mapper itself. There's a number of different architectures you can look at, and I won't go into the details of that. But fundamentally, a lot of people complain that there aren't really standards in CubeSats. There are even less standards in microsats. At least you've got some physical standards in CubeSats. So microsats are very much a Wild West. Many different suppliers, many different architectures, many different system designs. And as soon as you start getting larger, I'm going to talk a lot about total lifetime cost. Anybody heard my other podcast for satsearch? I was talking a lot about total lifetime cost. And when your satellite gets more expensive and the components you buy get more expensive, and because you're larger, your launch gets more expensive, you start getting driven towards redundancy, cross-strapping. And again, then you need to take that into account when you're working on your ADCS system, because ADCS is difficult to cross-strap, especially when it comes to reaction wheels. So not just size scaling, but a lot of people now are talking about constellations, both CubeSat and microsat. So are you doing a one-off, in which case, do you really need, as was raised earlier, do you really need to do all your design yourself? But then you also start asking, if I'm going to build 100 units, do I really want to be paying a license for actually control algorithms every time I launch a satellite? So there's some trade-offs to be made there. Interesting, brought up the vertical integration thing. I think this is a myth now. I mean, I'm from UK, and I have great respect for the SSTL guys, who were one of the fathers, or probably now the great-grandfathers of small sats. And they couldn't get hold of components. They were so new to the market. So they did everything themselves. A lot of people have been trying to copy the success they had. But the market has matured. There are now people like ourselves and other suppliers who are making units by the tens or the hundreds or the thousands. And we've invested in the manufacturing capability, the design for manufacture, design for test, the processes, the ERP systems. Unless you're building 1,000 satellites, your non-recurring is always going to be greater than just buying components or algorithms from a third party. So I'm a big fan of having a value chain where you depend on other people's investments to offer products. And again, it's down to the total cost of ownership. If you look at the price of one torque rod and you say, wow, that's expensive for a bit of wire wrapped around a tube of metal, then you're really looking at the system from the wrong point of view. You've got to think about how long it's taken someone to develop that system to achieve that cost. And then there's a great paper, which I hope some of you have seen, or if not, go off to the NASA website. It's a paper called Reliability of Zero. It's written by the name somewhere, Bill Purdy. And that was mainly aimed at not over-designing spacecraft to achieve very high reliability, but it also applies to buying things off the shelf. If your mission is to deliver a communication system, IoT, or is to deliver images to the ground, and you're a year late because you've spent all that time developing your own components or algorithms, during that year, your mission has zero reliability. You are not delivering any service. So, and you're also not generating any revenue. So I'm a very keen proponent of buying things off the shelf if they're available. Of course, if you have a very specific mission, you have no choice but to develop yourself. So if you are looking for a solution, here's my kind of go-to list of what I think should be your drivers. And of course, this is open to discussion, but I believe in scalable architectures. So trying to keep a similar spacecraft architecture, whether it be CubeSat size, 12U, 50 kilo, 500 kilo, 5,000 kilo. Basically, things need an actual control system. They need a communication system. They need a power system, a computer. So try and keep your architecture the same, because all companies are moving up the food chain and building bigger and bigger satellites. So try and avoid redesign time by having scalable architectures. And likewise, modularity. You want to be able to change out your actuators on your next mission. Technology moves on, suppliers disappear. So keep a modular system that allows you to chop and change. And then, yeah, lessons learned and mistakes people make. I mentioned there aren't standards, but I mean, people do use I2C, people do use RS422 and SpaceWire and things. Make sure it's the standard. There are people running UARTs at non-standard speeds. There are people using CAN bus with different clock rates. And a mistake lots of people make is they assume if they buy 5 different suppliers CAN bus interface components, so they can all work on the same CAN bus. Everybody uses different protocols. They put the address fields in different places. They put big endian, little endian. They put their data back to front. So you really need to take into account that buying 2 things with the same interface, you can't put them on the same bus. Vendor independence, I think, is really critical for the reasons I mentioned. So I'm just going to go through a few solutions. I have to say, despite the years I've had in the business, I'm not quite seeing where the market's going. So we're hedging our bets in new space and working in a number of different areas. And again, it would be great to get some feedback of which areas people are looking at. So I call those modular systems with algorithms built in, modular systems without the algorithms, and then a kind of catch-all, which is a hybrid between the two. So our good friends at Cubespace, who have just been talking, we work closely with them, and the nice thing that they've done is they've taken their heritage computer from their CubeSat system and their heritage algorithms, put it in a different type of box, added some modularity at the physical level, which they call Cube Connect, because they call everything cube something. And that allows you to then basically be vendor independent. You can plug in anybody's wheels or magnetometer, so it doesn't have to just come from them or just come from us. And then it gives you a standard interface back to the onboard computer. They also offer the service of doing the simulation of the mission for you to make sure everything is sized right. So it's a very easy way of coming in and buying a microsat-sized system. The downside is that, yeah, it comes with these algorithms. There is some modularity, so you can develop your own, but you basically are stuck with the computer that comes with it, and not too much flexibility in the algorithm development. So that then comes the hybrid version. We're working with another company in Germany called Spin. They have a nice box called Magic, which is based on a dual-core Geisler GR712, which is a rad-hard processor. They have developed a number of drivers to talk to a number of different vendors' components, including our own, but they leave the ADCS software to yourself, or you can work with one of their partners to develop the algorithms and then port it onto their machine. And being dual core, it's quite easy to integrate because you run the ADCS on one core and their drivers on the other core, and potentially you can actually use it as the overall onboard computer for the mission. And then the way I'm betting things will go, just because of background, anybody who's not familiar with the ESA speak, an RTU is a remote terminal unit, and the traditional way of building a big satellite is you choose your actuators and your sensors, and then you build a dedicated box that interfaces all that complexity of different interfaces to a single interface that talks to your computer. So we've come up basically with a bit of hardware which doesn't have a processor in it, but it is a packetizing system, so you can talk directly from one end of the system to the other in the native language of what you're talking to, and the routing and the packetization takes care of all that. So that's transparent to you. And because it's a routing system, you can have multiple sources and multiple targets, and automatically reroute those, so that if you have a redundant system, you can choose which processor talks to which system on which port. So it's a very, very flexible piece of hardware that, well, again, means you're vendor dependent, modular, and a scalable architecture. So in conclusion, yeah, look at total ownership costs. So don't just look at the cost of the individual components. Look at how that fits within your non-recurring cost, your launch cost, your mission cost, your payload. Everything should be balanced. You shouldn't save money in one area because it's going to cost you more money somewhere else. Look at scalable architectures, look at modularity, which means independent of particular vendors. Forget about this myth that you have to do everything yourself. The market is mature enough now to have good supply chains. And if you need to buy something, you'll find someone competitive, because there are a lot of people entering this market now. Think about time to market if you're an operator, or you're even if it's science, or even if it's a university mission. You know, you want to get your mission up there as soon as possible. Otherwise, your PhD or your thesis will be over by the time you get in-orbit data. So constantly think about your total cost of ownership, both financially and schedule-wise. Thanks very much. That's all I had to say.
Great. Thank you very much, James. Some really interesting insights on the challenges of scaling up and the opportunities of scaling up to larger satellite sizes. So that's great. Thank you. Next, we have Jakob Nissen, Chief Sales Officer of Space Inventor. There you go, Jakob. I see you've already shared. So
yeah,
thank you.
thank you. You can see my screen.
Yep.
I just find a way how to operate. Here we go. So I will not talk about too much about Space Inventor itself. We are based in Aalborg in Denmark. We are specialized in both CubeSats and microsatellites, and we build complete satellites, including the ADCS systems. We are also very much involved in projects and missions where very accurate pointing requirements exist, and also with very low jitter applications. One of the other things that we are working on is also a little bit more challenging ADCS systems, where you are going to GEO, where you need propulsion systems to do your orbit transfers and orbital maintenance as well. But we'll go directly into most of the interesting points, and if you want more about Space Inventor, then go to our website and have a look at our products and our history. I think one of the things we will go through is all the different aspects of designing the ADCS system. And as some previous speakers has talked about, is if you want to do this right, then you always start with your requirements and make sure that you actually are defining the right requirements for your mission, and you are not just taking the best opportunity or the best numbers you can find on the internet and then put that into your requirements. So I think, as like Cubespace said, this is a kind of an art where you are balancing the requirements with the system requirements and mission requirements, and then try to make a good balance with your mission operations and your ADCS systems as well. One of the things we see quite often is that people are putting a quite strict requirement to your pointing, but if you have, for instance, a communication mission with an antenna with 80 degrees of opening angle or beam width of your antenna, then there is no point of making a 0.1 degree accuracy of your pointing. That will just add a more cost to your mission as such. And I think also one of the biggest mistakes when doing the requirement specifications is to talk about, is it 1 sigma or 3 segments, because these kind of numbers will have quite a big impact on actually the cost of the ADCS solutions at the end. So from our point of view, as James talked about, it's that the ADCS system needs to be a kind of a generic approach, which we are taking with a very distributed open architecture with the distributed software components that we can program in orbit. But for our point of view, ADCS is the most complex system that you have on the satellite bus. I'm not talking about the payloads, but for the satellite bus itself, the ADCS is a critical point. And also what we hear also today, and mainly in the entire, I would say, CubeSat industry, everyone is so focused about the hardware and what are the different performance of the hardware. And actually, in an ADCS system, the software is the most critical item you have in the system. You need to have reliable software that are robust for different sensor errors in your actuators, etc. So you will actually have maintain and mission operations during the lifetime of the satellite. So I can only point out that, yeah, software is a very critical topic or point in the ADCS system. So when you are scaling your system, of course, you need to figure out what kind of pointing requirements you have. And for me and for us, we are more or less determining whether we need star trackers in the system or not. So if you are going below 0 or around 1 degree pointing accuracy with 1 sigma, then you should consider having a star tracker into your system. And if you have really strict requirements, then you probably need 2 star trackers if you need accuracy on all 3 axes. Also, it's not only the size of the satellite that will scale how large racks and wheels you'll have. It is also, what, as mentioned before, what kind of maneuvers do you want to do with your satellite, and how fast are you doing all the maneuvering. So the faster you need to do the maneuvers, the larger wheels you will have. Also, pointing modes for your software is also quite critical for designing your ADCS system. And also, how does your ADCS system actually also work together with your power intake? We do solutions where we can do nadir pointing while we are doing power optimization with the free, what's called axis.
Yeah, the last free degree of freedom.
Yeah. And then finally, also propulsion systems is something you should also consider when you're doing the ADCS system. I need to do some orbital maneuverings and station keeping in your orbit. Then it might be worthwhile doing propulsion systems. Otherwise, you need to go into drag management as well, which is also a possibility. So we provide all kind of products for star trackers down to 1 arc-second. We do big range of racks and wheels, from very small for a 1U or 3U satellite up to 100 kilos of satellite. So big range for our racks and wheels as well. Some of the performance we are looking into is stability and jitter of the entire mission and the ADCS system. And of course, as I said, software is quite important to actually control the entire ADCS system and make sure that you actually also can combine how the ADCS system works with also the different payloads. So you can actually control that you run in a very stable mode while you are taking images. So you will reduce your jitter. And then, of course, one of the biggest contributions to jitter in your satellite is the racks and wheels. So make sure that your racks and wheels are being balanced very precisely. At Space Inventor, we are balancing our own wheels very precisely. When we are balancing the wheels, we are actually putting some pen markers on the wheels, and we have to compensate how these dots are made on the wheels, because if they are not equally spaced around the wheel, then we can measure that just the weight of the ink of the pen. And also what the other people have said, regarding the performance, it's very nice to have simulation tools that actually can simulate how is the ADCS system working in this specific orbit. So you can actually see how all the maneuverings is doing, and how your control loop is compensating for the different disturbances. One of the things we've done as well and seen as a very nice feature is that we can actually also run our simulation tools on the hardware itself that will do the calculations. That means that we also are eliminating different implementations that are done on the physical hardware that will fly in space, quantization errors, etc., that will exist on the computer itself. Some of the lessons learned as well when we're going into the integrations. I think it was also mentioned before that field of view of the different sensors need to be taken into account, and also that reflections from solar panels or deployable solar panels are not being making distortions into your sun sensors, for instance. Otherwise, we need to make sure that the different zones of the mission. So sometimes you need to make sure that the star tracker is not in the sun. Yeah, and I think finally, I can't remember who mentioned that as well, but one of the things we've seen is coordinate systems is also very, very important to keep track of, especially if you are integrating everything yourself. You need to make sure that the different sensors that you put on the different panels are registered and make sure that the coordinate systems are being aligned with your software. Also, one of the things we've seen for selecting an ADCS system is actually how easy is it to do the commissioning of the ADCS system. How quickly can you get it and how can you tune it during the orbit? So having the right system with a very open and you can say easy access to all the parameters in the system will actually save you quite a lot of money and time when you're doing the in-orbit systems. One of the things we also done is to make sure that the commissioning is done more easily, is to make sure or actually automate some of the calibrations we have, especially our magnetometers. And then also we have done quite a big an effort of making it very easy for doing in-orbit tuning of the ADCS systems without uploading new software, but just changing the parameters of the systems. With the system we use with a parameter system, we can actually also, during an orbit, change, you can say, how fast the ADCS software should react on the different maneuvers that we're doing.
Yeah, gains and everything like that are easily tunable.
Yeah. So also on lifetime, I think we have some of the usual suspects for the wheels. That the more you use the wheels, the shorter lifetime it will have. So if you have quite a lot of maneuverings that requires a lot of torque, then that will also impact your wheel lifetime. One of the things we are doing for expanding the lifetime above the 5 years that we normally have is to run the wheels as momentum wheels. That means that we are biasing the wheels, so we will only operate without having any zero crossing of the wheels. That will have an extremely impact of the lifetime of your wheels. Then also for the start trackers, sorry, we actually for the start tracker are using red hardened components, and that's actually the only component that we have in our geostationary satellite missions. That's for the start tracker. So all the optics we use is for red hardened, so it will not get darkened by the light and radiations. And also the sensor is a red hardened component because it is exposed to quite a lot of radiations since all other electronics are more shielded by alloy inside the spacecraft. So be aware of the optics for the Star Trek and the sensor as well, especially if you want to have a longer lifetime of your satellite mission. I think that was a very short introduction and go through some of the experience we have. If you are getting more interested in the products we have, you're more than welcome to send me an email, and I'll be happy to answer all your questions you might have.
And of course, we're available in the Q&A system as well.
Yeah, thank you.
Brilliant. Thank you very much, Jakob. That was great. Really interesting. Next up, we have Thomas Jens, the CEO of Tensortech.
Hello.
Hi, Thomas. It's sharing there.
Hello.
Great. Perfect. Thank you.
Right now?
Yeah.
Okay. So good afternoon, ladies and gentlemen. It's my honor today to be invited here to give you a sharing about a guide for selecting an ADCS for your satellite mission. And so what is the objective of engineers? And here the engineers, I'm referring to the people who are working for the satellite owners, that the company who own the satellite and they have to build the satellite and operate the satellites. So I believe their first priority is to extract value from these satellites. So these engineers should be focused on the payload and how to utilize the satellite buses to get the payloads to have its optimal performance. So this comes to an important question that I think many people are mentioning and explaining for it, is about how to determining the pointing requirements for your mission, because this is very important to get the best use of your payload. So criteria including like the pointing knowledge of your individual components, such as star tracker, or the pointing knowledge of your whole ADCS. So here are a little bit different, because like if you have a star tracker, and while this star tracker is installing on your integrated ADCS or your self-built ADCS, there will be some misalignments of these components. So usually the pointing knowledge of your ADCS will be lower than the component level. And then while you are installing this integrated ADCS into your spacecraft, there will be another misalignment. So the overall pointing knowledge of the spacecraft will be lower. And if you are installing a payload onto this spacecraft, and then the pointing knowledge or the pointing accuracy of this payload will be lower. So these are things users should be keep in mind while you're making your criteria. And then there are absolute pointing accuracy and relative pointing accuracy, where the relative one is usually referring to the jitter. So people are maybe less familiar with the relative pointing accuracy. So actually this is a drift of attitude defined by a period of time. For example, like 30 seconds or like 1 milliseconds, depending on the user's application. So usually we have a scenario that's optical payloads that are taking images to the Earth. So these image or these cameras, they have exposure time to capture the image. So if the satellite's attitude is shaking while taking images, then their resolution will be of the image will be some degradations. So while you are building a remote sensing satellite, the relative pointing accuracy is a very important criteria. And there are also slew rates, that how fast can your ADCS to change the angular velocity of your satellite. So let's break down to different types of satellites. So there are the remote sensing satellites. If you have a narrow field of view, then the absolute pointing accuracy will be very important, because if your satellite is drift too much away from your targeted object, then your target object will be out of your the field of view of your camera. And there are communication satellites. Usually they require less sophisticated ADCS, because their pointing requirements are usually lower than the remote sensing satellites. So for example, if you are using a UHF antenna, and usually these antennas are omnidirectional, so you didn't need to have a good pointing requirement. And so even if you are installing expand antenna on your satellite, and then if you have 4 degrees of angular deviation, then they only cost 0.1 dB of losses for the antennas. And the higher the communication frequency you are using, and usually this antenna requires requires a better pointing accuracy. But for most of the CubeSat satellite mission, people may use S-band antenna or X-band antenna. So usually you maybe don't need a pointing accuracy that's better than or 1 degree or 0.1 degree. And if your CubeSat has something like a deployable antenna, and you should be watching that if these ADCs should be able to provide a maneuver to let the solar panels to capture the sun. So after knowing the pointing requirement of a mission, here comes to several different methodologies of building an ADCs. So traditionally, people used to design and build manufacturing every component from ground, and then to integrate their whole system. So this is the old days, the space agency driven days that people cannot find available vendors from the market. So they build everything from ground. And then since the space industry becoming more and more mature, and then the dividends of labors are getting more and more professional. So there are some vendors provide a commercial out-of-shelf components, so people can pick up the reliable components and integrate their own ADCs. And according to our investigation, that most of the CubeSats are built by the second methodologies nowadays. But there are also another trend is popping up that people started to purchase integrate ADCs, which the vendors help the people to integrate everything all together from the components, and then help them develop the firmware, the algorithms, and then also the calibration. So the users does not require to build the ADCs everything by themselves. And I believe this is a trend for the market, because everything's are getting more and more professional. And then there are also always the fourth method that you can always hire a contractor to build your satellites. And these contractor could purchase components or purchase the integrated ADCs and build ADCs for you. But today's talk, I will be focused on method 2 and method 3 majorly. So if you are adopting methodology 2, that you are buying components and integrate your own ADCs, there are a couple of things you should be aware of, including when you are picking up a reaction wheels. There are some specifications that are other than the angular momentum or the torque. These are the magnetic disturbances specification, and also the imbalance of the rotor, which is the major contributor of jitter. And then when you are choosing your attitude sensors, especially you are choosing the image-based one like Star Tracker, and then they usually have a lower update rate. So these sensors usually limits your bandwidth of your control system. And if you wanted to have a better update rate, then your power consumption will get larger. And so while you are implementing your own ADCs, there are system errors that quite often occurs for these self ADCs builders, because when you are trying to align the different component frames, even you are using locating pins, and then the sensor will have some deviation or misalignment while installation. So this causes the degradation of your overall performance. And also there are the nature of the components. There are random errors for these attitude sensors. And then if you are implementing the algorithm by yourself, and then there might be some human error that your algorithm may have some blind spots, or may behave not the way you think it will be in space. So it's important to have a software in the loop simulation, and then also a hardware in the loop simulation. But both of these two methods, it's hard to validate the relative pointing accuracy. So it requires people to take efforts to get the things to be done with a reliable way. So here's the introduction of the pros and cons of using integrated ADCs. That's they are usually more expensive than you purchase the individual component and integrate the system by yourself. But of course, there are also benefits, because you don't have to develop the algorithms by yourself and do a calibration, and then it saves you manpowers. So, but if you count in these equipment costs or the manpower cost and time cost, in fact, maybe integrated ADCs would be a more reliable and economical choices for you. And here I divide the ADCs into three categories by its pointing accuracy. And there are purely talker-based ADCs. They are just around 10 degrees of pointing accuracy. And then there are a reaction wheel based, but without star tracker. And the one with star tracker, which is the most expensive and the most sophisticated one. And these different ADCs are different by their cost, of course. So finally, I would like to introduce you with several findings that I observed on the trend of this ADCs industry. There are some companies are developing the system identification methodologies to determine the mass properties information on orbit using their developed software. And then there are Agile satellites that are utilizing CMGs, control moment gyros, to have a better slew rate compared to the traditional solutions. And then better components always driving the technology to go further. So there are attitude sensors with a higher update rate. And then here I'm going to introduce you with Tensortech's unique offer, a control moment gyro that is based on a spherical motor. So this spherical motor-based CMG is comparatively smaller than the traditional CMG because they utilize a multi-axis actuator, which can provide people with a smaller volume weight with the compared to the traditional solution, which is the one you see in the picture here. So yeah, this is my presentation today, and thanks for your listening.
Great, thank you very much, Thomas. That was great insights there. Thank you. And then finally today we've got Arnie Brothers, the embedded software engineer at Cubespace. So
Yes.
Arnie, it's perfect. You're sharing your screen. Thank you.
Yeah, now the presentation should have popped up. So, hello everybody. My name is Arnie Brothers, and today I will guide you through the technology and the vision of Vieren on control moment gyroscopes. So, something that was briefly mentioned by Thomas before. So we will try to educate you about what control moment gyroscopes are. For those of you that don't know what they do, how they function, we will briefly go through the hows and whats of CMGs before we focus on what Vieren has to offer as solutions with CMGs. So Vieren is a company founded in 2016, developing its core skills and competence in in-orbit mobility. So as a young company, we started with our focus on satellite attitude control technologies, more specifically development of CMGs for small satellites. And with small satellites, we understand small satellites smaller than 500 kilograms. I am Arne Brothers, so as mentioned before, the embedded software engineer of Vieren. And currently, I am mainly busy with the firmware for our CMGs. So, what is a CMG? A CMG mainly consists of a wheel that is mounted on a certain axis that can spin. This we will call the spin axis. And the core functionality of a CMG lies within the ability to control the direction of this axis. So we need some kind of rotating platform that can reorientate this spinning axis. In real life, we then get something like this, which is the CMG that was used for the ISS space station. And obviously, this would not fit a small satellite. So we came up with this. And as you can see, we here have a spinning wheel, which we can reorient with a small platform. Now, how does this work? So when we spin a wheel, we create a angular momentum, which is held by the wheel that is spinning. And by reorientating this wheel, so by turning the spin axis of the flywheel, a gyroscopic torque perpendicular to the angular momentum will be created in the plane of rotation. The amount of torque is determined by the rate of change of the angular momentum, thus the speed with which we rotate the platform on which the wheel is mounted. By controlling the direction of this angular momentum, we can interact with the total angular momentum of the satellite, which allow us to influence the attitude of a spacecraft. And here you see what this looks like in action. So quickly try to pause. Well, here we have 4 CMGs. So as with reaction wheels, we need 4 CMGs to create a full momentum envelope. And we can see here, so the wheels spinning on top of the rotating platform, which are reorientating the direction of this spin axis of the wheels. And then in this case, for a Earth observation mission, we can reorient the, yes, we can control the attitude of the satellite in its orbit. Now, our sales team has noticed that the awareness of the existence of CMGs on the market for small satellites is not always present. And when searching for actuators, often the search is done with reaction wheels as a keyword. So we made a small overview of the 2 technologies to compare how they work and what they do. So CMGs and reaction wheels both rely on the principle of momentum conservation. With a reaction wheel, this momentum is fixed in the direction of the spin axis, while with a CMG, we can redirect this direction of the momentum by turning the rotating platform. And since the change of angular momentum creates torque, the change of magnitude of this angular momentum makes or creates the torque in a reaction wheel, while in a CMG, this is done by reorientating the wheel, so by moving the direction of this momentum. And for those of you involved with electromotors, you can directly see that in terms of power consumption, a CMG, so rotating a wheel at a constant speed, will be much more efficient than spinning a wheel up and down constantly. So yeah. So what did we do? We had a good look at the bigger example. We miniaturized it, and this is what we came up with. We believe that the CMG is the most performant actuator type for attitude control in small satellites. For example, to reach the performance of a CMG, you could boost the reaction wheel through playing with the input voltage of your reaction wheel. But even boosted reaction wheels will not suffice to reach the potential of a CMG. Yeah. Also, we have a small lead time, and everything is ITAR free. Currently, where are we with this technology? So we are almost ready to step into the market with 2 CMGs. We are currently planning an IOD for the second quarter of 2022. As you can see, the technology is de-risked with the support of the European Space Agency. So most of these pictures are also from the test facilities of Aztec in the Netherlands at ESA. Our approach also involves modularity, as already mentioned by James. So we approach the CMG actually as a scalable building block. This means that for performance requirements that cannot be met by a cluster of 4 CMGs, we can equip bigger satellites with a multitude of CMGs that are similarly oriented. So yeah, for example, we can fit up to 16 CMGs in a big satellite. You also see mentioned in the slide that we target satellites from 50 to 500 kilos, and you can ask why won't we go smaller than 50 kilos? Our modular approach involves that we have some components that will not change when we make the CMG smaller. So for targeting smaller satellites, you would only need a smaller wheel, but the rotating platform and the control electronics, which are part of one module, would not shrink. And that's why we believe we found a sweet spot with our micro CMG, one of the two models I will introduce, where we found a good balance between the mass of a module and the potential torque it can deliver. So this is our micro CMG, which we like to compare with a 1 NMS reaction wheel. And for those of you familiar with reaction wheels, you can see for the mass and the peak power and the momentum the wheel is holding, we can create a lot of torque. The same can be said for its bigger brother, which we call the mini CMG, and compare it to a 4 NMS reaction wheel. Where for the same story, for the mass, the peak power, and the momentum it holds, we can create a lot of torque. Both CMGs are equipped with a COM interface. UART can be implemented on request. And currently we have 2 engineering models available. Or the both models are available as engineering models, and flight models will be available close to our IOD in the second quarter of 2022. Now, what do you get when you combine 4 of each model to have a full attitude control system? Well, along the pitch, roll, and yaw axis, you can get for micro CMGs almost 2 NMS, and for mini CMGs above 6 NMS, which then can create 1 Newton meter along each axis for micro CMG and more than 3 Newton meter for the mini CMGs. The peak power mentioned is if we do a maneuver at or maximum speed along or around one of the axes for 1 second. And for a cluster, you then come to approximately 7 kilos for the micro CMGs, 11 kilos for the mini CMGs. We also want to mention that CMGs are not or it's not a technology that should be exclusive to your, or if you choose for CMGs, that it should not be exclusively CMGs in your attitude control system, but that CMGs can be combined with reaction wheels. So they both rely on the same principle, so you can combine them. This can, for example, be the case in missions where you have you need more agility along one axis than another one. Our modular approach also involves that you can arrange these modules in your satellite as you want. So on the left we have an array approach. On the bottom we have a linear approach. And the right top is actually demonstrating that every CMG can be placed in a different location in your satellite. So every module holds its own communication and control electronics. So it's perfectly possible to scatter them through your system. Yes, and this is the end of my presentation. I want to thank you for your attention, and if you have further questions or require more information about CMGs or what we can do for you, you can always pop a question in the Q&A or contact me by email. And yeah, I hope you learned something more about CMGs and what they could mean for your control attitude system.
Thank you, Annie. That was great. Thanks very much. I'll just say a few brief words to finish up, but while I do, please do feel free to submit any questions you might have for ViaWare based on that presentation that you've just viewed, or indeed for any of the other presenters today. So firstly, thank you to all 6 of our presenters today. I think you've done a great job explaining how an ADCS works in space missions and what engineers need to take into account when selecting and using them. Just to go through a few of the highlights quickly, I think we've learned about how to develop better pointing requirements, advice on the trade-offs in component selection, the buy versus build-in for ADCS, integrated ADCS, testing and integration. Sorry, put my teeth back in. Testing and integration, and the importance of simulation tools in particular, scaling up to larger satellite sizes, trends in the ADCS sector, CMG technology. We've you guys really packed a lot in, and we actually are almost bang on the 90 minutes, which is great as well for everybody's time here. Now, we've all had to get used to more online events over the past 18 months, and hopefully you agree with us that the format can really bring huge value. I think the depth and the quality of the information you've heard today demonstrate that, and you didn't even have to leave home to hear it. So if you have any further questions or feedback for us or the presenters after the end of the event, please feel free to reach out to them or contact us at info@satsearch.com. We'll make sure every message gets a response. As mentioned, we'll also follow up with you with the footage and the available slides soon by email too. And if you'd like to hear more insights like these from people working, at the cutting edge of the industry, we also run a weekly podcast called The Space Industry. James mentioned it in his speech. He was the most recent guest that we published there. And you can find it on all good streaming platforms and on the SatSearch blog too. And, we have a weekly newsletter that shares trending news stories in the industry and updates on both our members' work, like the developments you've heard today, and some of our own work as well. The link to sign up to this should hopefully be in the chat box there. Yes, it is. So yeah, that's it. Thank you very much to everybody. Thank you to all the presenters and to everybody listening with us today, and have a great rest of the week and the weekend.